everyone, it's Julianne
And Berna.
and we wanted to take a few minutes to explain how you're going to process the data that you've now collected on your ant species. So what we wanted to do is we wanted to create a video that you and your group could use to take you through step-by-step how to do your calculations. So the intention of this video, we wanted to provide you with a tool that you could watch a little bit of and then pause. You could watch a little bit more and then pause. And actually, you might even need to watch it a couple of times to see how to do the calculation. The idea being is, you could watch it once all the way through with your group, and then just to get a big picture of what you need to do. And then when it comes time to doing the actual calculations, you can watch a little bit and then pause to do your calculations, watch a little bit more to do the next step. So we're going to take you through step by step how you're going to come up with a quantitative representation of biodiversity.
Ready to show them how?
Let's do it. Let's do it. All right. So ecologists have an actual formula. They have an actual tool that they use to represent how biodiverse an area is. So it's a formula that we're going to take a look at in just a minute, but it's called the Simpson's Biodiversity Index. And again, this is going to be an actual number that you're going to calculate that will give you a quantitative figure that represents the biodiversity of a particular area. So for this project, you're looking at a particular question.
How is biodiversity and abundance of ants affected by human activity?
You and your group came up with a hypothesis. You were sent out in one of these three areas. You were either sent out to an area that has low human disturbance, medium human disturbance, or high human disturbance. And you hypothesized what you thought the impact of those disturbance levels would be on the ants. So maybe you talked about, you thought in an area that had high disturbance, maybe you thought that biodiversity would be a little lower in those areas. What we want to do now, you have all that data that you collected. Let's do some mathematical calculations to see if your data supports the hypothesis that you came up with.
Always comes back to numbers.
All right, so this is the equation that we're going to use.
Yeah, so I want to kind of hit a couple pieces of this because when people look at equations, they automatically look at the symbols and get a little confused. But each of these pieces has a certain meaning, and Julianne's going to go over how it actually works. But just kind of really quickly, the D stands for your diversity. We'll explain why you're subtracting this from 1. And then this symbol right here, the Greek capital sigma, means sum. So this is summing up. We have a product in the numerator, and then we also have a product in the denominator. So as we do each of these calculations, we're going to be summing that product up.
All right, so out of all those pieces of the equation, maybe I should show you. Back here we had a little n and a big N, or a capital N. So I'm going to refer to them as the little n and then the big N, and we'll take you through what those represent. So the first one is little n. And what little n represents is the number of individuals of a particular species. All right, so when we were looking at our ants, you classified them into different groups. And for now, even though we didn't, identify the species of ants, we're saying each of those different types of ants represents a different species of ants. So little n is going to be the total number of a particular species of ant. So on your data table, it's not important that you can actually read these numbers, but instead you have a data table that looks very similar to this one. This is the data table from last year's students who did something similar. So as you can see over on the left, that's a list of all the different types of ants that were encountered. All right? And then we looked at, let's say, we're looking at, actually I think I said medium disturbance. All right? So these are all the different types of ants that were found by the different groups that were studying medium disturbance. So the little n is the total number of each of those same type of ants. So if we go across the row, we're going to add those together. So we have one group found 2, another group found 33, and the last group found 5. We're going to add that row across, and 40 is going to be our first little n. And then we'll go down, then there are a bunch of ants that, there weren't any. We'll go down here to this next one. All right, all the ants in this row, 147 plus 18, that equals 165. So each of these represents a little n. It represents the total number of a particular kind of ant that we were looking at. Now for the big N, all right? So big N, that was at the, what's that, the numerator and the denominator?
Denominator.
The denominator, that was on the bottom of our equation, and it represents the total number of all the ants. It doesn't matter which species it is, it's all of the ants. So now what we're gonna do, if we were still looking at medium disturbance, we're going to add up all the ants in this column, and at the bottom of the column, once you add all these numbers together, that's going to give you your big N. That's going to give you your total number of ants. So in this case, we had 40 plus 165 plus 4 plus 11 plus 6 to come up with 226. All right, so those were the big N and then the little n. All right. So those were the big N and then the little n. Now we want to see how this fits in this equation here. So Terry mentioned that this is the Greek letter for sigma, and that represents the sum of. So if you look up here in our equation, we've got the sum of little n times little n minus 1. But the sum, what are we adding together? We're going to add together all those little n's, all right, in our equation. So we're actually going to do this equation out. So we're going to do this, the numerator first, all right? So we're going to take the sum of little n times little n minus 1. So our first little n for this one was 40. So it's going to be 40 times 40 minus 1. Otherwise known as 39. Plus, remember, sigma. So now we're going to add that to the next little n, which was 165. So 165 times 165 minus 1, or 164. Plus, down here, our next little n is 4. So 4 times 4 minus 1. 3, plus, we've got 11, so 11 minus 1 would be 10, so times 10. Then our last one is 6, plus 6 times 6 minus 1 for 5. All right. This is a part where you probably need a calculator because you're going to go through and you're going to multiply all these together, all right? And you're going to come up with those values. So 40 times 39, if I do that in my head real quick, I think that's around 1,560.
Wow, that's really good, Julianne.
All right, plus 165 times 164. Well, that sounds like 27,060. Plus 12 over here, plus 110 here, plus 30 right there. So now all those values, that's what we're going to add together. So that's what the sigma represents, is adding all of those little n's together. All right, and so if we were to do that, if we were to add all of that together, that would give us 28,772. So that's the numerator. Now we have to figure out the bottom of the equation. That was big N times big N minus 1. Notice there's no more sigma because there only is one big N value. So that's the 226 down here. So right here we're going to do 226 times 226 minus 1 is 225. So then if I think about that real carefully and do some calculations, that's around 50,850. So now we're going to go ahead and divide those numbers. And if we do that in our calculator, we should end up with a number that is 0.56. All right, almost done. Not quite done yet. We've got this value, but you'll notice in our equation, we have 1 minus all of this. So our very last step, we're going to take 1 and subtract it from that 0.56. That's going to be equal to D, so our diversity index. So if we go ahead and we do that, that's going to give us a diversity index of 0.44 for our final answer. And remember that this was for medium disturbance. So for medium disturbance, we got a diversity value of 0.44. So now we have a quantitative measure of how diverse the area is. But what does that number mean? How do we go about interpreting that data? So the next step is we have to go ahead and evaluate the data. So we need to know, was that number of 0.44, does that represent high biodiversity or low biodiversity? So the closer the number is to 1, the higher the biodiversity. The closer the number is to 0, the lower the biodiversity. So if our diversity index was 0.44, that number's closer to 0 than it is to 1. So we would say that this represents a lower diversity value. So what your job is now is to go through using the data that's been generated by all of the different groups in the high, the medium, and the low disturbance areas. Your job is to go use that spreadsheet to calculate this biodiversity index for these 3 areas. So when you and your group are going to come up with an index for those 3 areas. And the idea is that using then those values, you're going to know whether or not, as a whole group of all of these students, if we were able to gather data that supported your hypothesis. What you might be wondering though is, how does this crazy equation actually work to give us this diversity index? So I'm just going to go back for a second to a slide that has the equation right there. And I don't know, Terry, can you give us some insight? How does this actually work?
Absolutely. So this is the bonus track. So if you want to know how this works, it's always a good idea to see how formulas work. So you now know how to use it, but now this is how it actually works. This is actually a probability statement. So if I remember probability, so probability is success out of total, right? So the success out of total. And our success here would be like brown ants or black ants or the little mini red ants or any of those different types of ants that you saw out of the total number of ants that we collected. So let's say that we were doing little brown ants. I would say, well, I want to know what is the likelihood of getting a brown ant. Well, then that likelihood we're going to call N, and I'll put a little b there for a brown ant. And the likelihood would be out of the total. So now out of the total ants. But the diversity index works as the likelihood of getting 2 out of the group. So now if I've already taken 1, we always assume success, the next one would be N minus 1, because I have N minus 1 ants left in, out of my total, N minus 1 total ants. Then we would look, well, we had many different species. So we had the black species, we had what other species are there? So black,
there's an orange. There was large, there was small, yeah.
Yeah, so there's a lot of them. So here I'm going to say or, and in probability, and I'm going to say that these are little black ants, in probability, or is indicated with a plus. So then I would look at the next ant. So let's say the red ones. So what's the likelihood of selecting a red ant out of the total ants? And so I'm still looking as out of the total. And then I want to look at the likelihood of getting a second red ant out of the total ants. So I'm going to say times little red minus 1 out of the total minus 1. And I'm going to keep on doing that until I get to all the ants. So we go all the way to whatever the last ant is, red, black, I don't know.
Orange.
Orange, we'll call this one orange. And this is how we actually get the formula, because we're summing it up, so we're adding all of these together. And so since we just indicated it with a little n, that's fine, it just represents all of them, so it's no big deal. And we just add them all up. Notice the denominators are exactly the same in each, which is why you could write it like this. And so this is actually, without this 1 minus, the likelihood of selecting 2 of the same species out of all of the ants. When you do the 1 minus, well, if this is the likelihood of picking the same, we want the likelihood of being diverse or different, so we do 1 minus. That's the bonus track. That's why it works.
It's amazing.
It's amazing.
Who knew?
I didn't know.
All right, so again, the idea here is you kind of watch this, you pause it when you need to, you kind of go back, but hopefully this will guide you as you go about completing your calculations to determine the biodiversity of the ants in those 3 different areas. Good luck.